Assalamu alaikum. So, under the convex optimization problems, you have many types of problems. One famous and popular problem is called the linear programming or the linear optimization problem. In LP or linear programming, the cost function is linear with respect to the variable x, and also the inequalities are linear here, right? So, but you should note that here uh, you have a vector c multiplied by x, whereas in the constraints you can have a vector or a matrix multiplied by x, right? So here you have a linear cost function, and you have m, let's say here, m linear constraints. So LPs can be solved by what is called the simplex method. Okay, so the simplex method depends on the geometry of the problem. So if we uh, visualize the problem, I think we have shape here, right? So for example, what is an NP problem? NP problem is that you optimize C transpose X. This is a plane, right? This is a plane. If you don't constrain this plane is infinite. But if you constrain it by AX less than or equal B, you are constrained in many directions. So each line here is a constraint. So this is a constraint, this is a constraint, this is a constraint. So each line is one row of this matrix A. Okay, and this plane is oblique, so it's not horizontal, right? So you have an angle with the horizon. So logically, the minimum value should be at one of its vertices. So it might be here, 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 here. So what does the simplex method uh, do is actually you try out, you compute the objective function, and each of those these at each of those vertices, and you compare them, because it is expected to have the minimum value at the vertices, right? So this is uh, in general the simplex method, but you can solve it using traditional methods, right? So as we used to do earlier, we find the Lagrangian, right? So we include the Lagrange multiplier here, then we simplify it in a bit or rearrange it. We find the dual problem, right? This is our dual problem here. This can be found by taking, as we said earlier, the derivative, the gradient, the Jacobian with respect to x, and set to 0. Then we can find x, and then we substitute back into the Lagrangian, right, to find the dual problem. So the dual problem in this case is very simple, right? So this is like a formula here. So you convert a linear problem into another linear problem. So if the primal is a linear problem, the dual is also a linear problem with respect to the lambda or the Lagrangian multipliers. So okay, why should you find the dual problem here? So if the dimension of lambda, so let's say if the dimension of lambda is less than the dimension of the variable x, this means that the dual problem is easier to solve when comparing it to the primal problem, right? So you should solve the dual problem if the dimension of lambda is less, meaning that it's easier to solve, right? And mind you, the LP problem is a convex optimization problem, so solving the dual leads to solving the primal because we have strong duality. As an example here, right, we need to find uh, this the solution of this problem. As we said earlier, we can find it using the simplex method, and this problem is shown as we seen earlier in this figure, right? So this is the optimal value here, right? Okay, so let's take another example here. Let's find the dual of the LP problem. So we have this problem with two variables x1 and x2. As you can see, this is a linear combination of x1 and x2, and here uh, put you can notice or identify that the constraints are linear as well with respect to x1 and x2. So the first thing that we need to find is we need to formulate the problem in a standard form, right? So this means that the constraints should be inequalities less than or equal, not greater than or equal, right? And we can put them in matrix format. Then we need to formulate the Lagrangian, then find the solution using the KKT conditions, and as an extra task here we need to find the dual problem, right? Just for the sake of exercise, right? Okay, so we can put it in this standard form. So we need to find C and A and B. Of course, X is x1 x2 as a column vector. C here is the multipliers of x1 x2, so it's 1 and 2, right? A, here we can arrange this in a matrix format, so we can say okay, of course now we have x1 and x2. How many how many inequalities we have here? 3. So we have 3 rows. So the first one here is 1 1, right? 1 1, right? The second row is 1 0 0 1. Okay, what about B? B 2, right? For the first inequality, 0 and 0. Okay, but we have here greater than or equal. We need to multiply them by -1. So this becomes inequality less than or equal, right? So that's why we have this A here, right? And of course you multiply both sides by -1, so this again will will become negative as well, right? So we put the Lagrangian, right? How many lambdas we have? 3. Why? Because we have 3 constraints and 3 lines in A. Okay, so we find the KKT conditions. Of course, we take the derivative with respect to x. We adopt the inequality constraints, and we have the complementary slackness, of course, and always we have the inequality constraints. So we have those conditions here, right? This translates to, if you take the derivative to those equations, right? Again, this is the feasibility, right? Complementary slackness, this one, right? And this is the inequality constraints. So we need to solve for lambda 1, lambda 2, lambda 3, and x1 and x2. Okay, if you note here, we have 2 variables, primary variables x1 and x2, and 3 dual variables, lambda 1, 2, and 3. So it's easier to solve the primal problem, right? So this is the dual problem here, right? So as we said earlier, how do you find the dual problem? You take the derivative with respect to x, right? And you solve.